This is part 3 of lesson 6.1, Vectors in a Plane. We're going to start with an example from page 464, number 21. We are to find the unit vector in the direction of the given vector. So our given vector is u, and in component form it is -2, 4. And we want to find the unit vector. So what we're going to do is we're going to take the absolute value of u, so we're going to find the magnitude of u, because we need that. So we're going to do -2 squared plus 4 squared. And I didn't write the negative because it doesn't really matter, so I'm going to have the square root of 20, which is 2 times the square root of 5. And then to find the unit vector, I'm going to take 1 over the magnitude of the vector times the vector itself. So I'm going to take 1 over 2 times the square root of 5 times -2, 4. So I'm going to have -1 over the square root of 5, and then I'm going to have 2 over the square root of 5. Now, a lot of times with vectors, you don't have to rationalize it. You can leave it like that. We can also, if we want to, we can write this as the I and J vector, so you might see it like this. Depends on how you're being asked. If you're not being asked one way or another, you could put it either way, but usually you give it in the way the original vector was given. So the original vector was given in component form, so most of the time the component form is fine for the answer. Okay, more definitions, because that's what this whole section is about, understanding vectors. So next is direction angle. So the direction angle is the angle theta that our vector v makes with the positive x-axis. So here's where we're going to start connecting our trig to our vectors. So when it says resolve the vector, we're going to be resolving the vector. What that comes down to doing is if v has a direction angle theta, the components of v can be computed using, so we can write v in this way, the magnitude of v times the cosine of that direction angle, and then the magnitude of v times the sine of that direction angle. So let's use that in an example. So page 464, number 29, we are asked to find the components of V from this picture. Okay, so we're given a vector v, and we're told that this has a magnitude of 18, and we have an angle labeled here of 25 degrees. So we're going to use our formula. So v is equal to the magnitude of v times the cosine of theta, and the magnitude of v times the sine of theta. So we have the magnitude of v, which is 18. And we have theta. So we can just go ahead and substitute. So we're going to have v equals 18 times the cosine of 25 degrees, comma 18 times the sine of 25 degrees. So when we put that in our calculators, we get 16.31, comma 7.61. So that's how you can use the direction angle to find the component form of the vector. Okay, next example, number 33 on page 465. In this example, we are to find the magnitude and direction, angle of the vector. So now we need to work backwards a little bit. So this time we're given the component form, and we're going to work the other way. So the easy part to do first is the magnitude, so we'll do that first. So we're going to find the magnitude of v by taking the square root of 3 squared plus 4 squared. So we're going to get 5, because that's Pythagorean triple there. So then the x direction, we're going to have 5 times the cosine of theta has to equal 3. So cosine of theta is going to equal 3 over 5. So working backwards, theta is going to be inverse cosine of 3 over 5. So theta is going to be approximately 53.13 degrees. Because we can do that because here's our magnitude of v, and our cosine of our direction angle has to equal our component. So that's where we got that from. So we have our two answers here. We have our magnitude and we have our direction angle. Okay, we're going to finish this section by doing a couple application problems. So first one is going to be about velocity and speed. So now we do have to distinguish between them because velocity is a vector and speed is a scalar. So our first example has an airplane. Is flying on a bearing of 335 degrees at 530 miles per hour. So we are to find the component form of the velocity of the airplane. So really, this isn't that much different than what we did before. So the first thing we want to realize is we're given its speed. So with that, we know that the magnitude of the velocity is going to be 530 miles per hour. So that's the first thing we have. So the next thing we have to do is figure out the actual angle. Remember, theta isn't just any angle given, it's the angle made with the x-axis. So here's my north. This is north. Remember, bearing is how far it is from north. And let me just kind of sketching here my x-axis. So we're on a bearing of 335 degrees. So we're going to swing around here. That's 90, 180. We're going to be almost the whole way back up because we want at 335 degrees. So there's our 335 degrees. So what we have left here is we have this little angle here of 25 degrees. So what we have to figure out is how far is it from, let me use red now, from here all the way up to here. So we have a 90-degree angle plus that 25 degrees. So that gives us a theta of 115 degrees. So that's our theta. So now we can find the component form because we can use our direction, angle formula to fill in everything we need, because we have our magnitude, we have our angle, and we can just figure this out using our calculator. So we get the component form of our velocity is going to be negative 223.99, comma 480.34. Okay, next example, wind effect. So we have an airplane again. Is flying on a compass, heading of 340 degrees at 325 miles per hour. Okay, so now we have a wind is blowing with bearing 320 degrees at 40 miles per hour. So we have a couple things we want to do. First, we want to find the component form of the velocity. So that's going to be just like part A. I'm sorry, not part A, but the previous problem. Find the component form. Of the velocity of the airplane. And in the second part, I'll write it when we get to it, is we're going to want to see how the wind has changed from the ground, the actual speed and direction of the plane. So part A is going to be just like we did before. So when you say a compass heading, it's like saying the bearing. So again, here's our due north, here's our x-axis, and so we are on a compass or bearing heading of 340 degrees. So that means that this is going, the plane is actually here along this way. So we have a 20-degree angle here. 20, this is 340. Okay, so our actual theta is going to be here, which is 90 plus 20, so that's 110 degrees. That's our theta. So we already have the magnitude. So the magnitude is given by 325 mph. So we can go ahead and find our V for the airplane. I'm actually, instead of V, I'm going to use A for airplane because we're going to also take into account the wind here. So I'm going to use A. So A is going to be 325 times the cosine of 110 degrees, 325 times the sine of 110 degrees. So A is going to be negative 111.16, comma 305.40. Okay, so that's part A. So from an airplane's point of view, that's what's going on in the cockpit. So now in part B, we want to find the actual ground speed and direction of the plane. So what we have to do now is take into account the wind. So what we're given with the wind was, we were given that it has a bearing of 320 degrees at 40 miles per hour. So let's make a vector for the wind. So the wind, called W, is going to be 40. It's a terrible angle bracket because we're at 320. So it'd be the same kind of picture here, except this would be 320 and that would now be 40. I'm sorry, yeah, that would be 40. So we have 40, which is the speed. I was getting confused with my 40s there for a second. 40 with the speed times the cosine is now going to be 130, so it would be 90 plus 40. And then we'd have 40 times the sine of 130 degrees. So our wind speed, our wind component form, is going to be negative 25.71 and 30.64. And how do we combine the two of these? Well, we're adding two vectors. So what we're doing is we're taking our final velocity is going to be made up of the airplane plus the wind. So we are going to have, going back to our airplane, negative 111.16 plus negative 25.71, our wind, and then we're going to have 305.40 plus 30.6. Move this over so you can see it. 30.64. So simplifying this, we get the vector negative 136.87, comma 336.04. So we just have to find the magnitude of this vector to get the speed, and then use that to help us find theta. Okay, so let's start with the magnitude. So the magnitude of V is going to be the square root of negative 136.87 squared plus 336.04 squared. So our magnitude is going to be 362.84 miles per hour. So that's our ground speed. And now to get the angle, what we have to do is we're going to do what we did in an earlier problem, is we're going to work backwards from the magnitude. So we're going to do the absolute value of V times the cosine of theta has to equal the component in that, I'll just call it little v1. So we know that 362.84 is our magnitude times the cosine of theta has to equal our x component, which is negative 136.87. So solving that for theta, we we are going to get that theta is going to be inverse cosine of negative 136.87 over 362.84. So theta is going to equal 112 degrees. Now remember that 112 degrees is going to be from the x-axis, is going to be over here. So we have to subtract off this 90 degrees because we want the bearing, oops, I'm so sorry. We want the bearing from our due north, this whole direction around here. So we need this little part in here. That's what we need. So if we do 112 minus that 90 degrees, that's going to give us 22 degrees. So then where we really are, so we have 22 here, so we have to take all of this then is what we want. So we're going to do 360 minus the 22 degrees, which is 338 degrees. So there's our speed and our bearing. So there's our ground speed and there's our ground bearing. And I think that's a great way to end this lesson.